I'm going to start with a remark, as we are all interested in, or at least as this meeting series is devoted to the question of deeper level theory. Our understanding in our search for a deeper level theory is that the Schrödinger equation cannot be the starting point, and therefore, of course, also not the de Broglie-Bohm theory. Rather, we start with an ansatz for a deeper level theory and then derive the Schrödinger equation or the guiding equation, etc. So this is our understanding of what a deeper level theory should be. The outline of the talk is the following. In this sense of deriving a Schrödinger equation, for example, we look at models for trajectories from an ansatz which is generally known as quantum mechanics without wave functions. We heard that about that this morning from Howard Weizmann, and there's other people involved like Poirier, Beckett. And the question is, or what are the possible ontologies related to these ansatzes of QM without wave functions? And our proposal is a sort of quote-unquote cosmological solution. So in our solution, which we generally denote as a two-momentum approach to EmQM, for the guiding law, which I'm going to explain in some detail, and also for dynamical non-locality, as it's called by the Aharonov group. We sometimes use the short term of switching, and I'll explain what we mean by that. And we are going to argue that we can talk about non-local influences which still are no signaling influences. As every theory, we also have some more or less implicit or explicit metaphysical assumption to start with. In this sense, we consider a starting point the Big Bang, or at least the existence of some kind of vacuum energy or dark energy, in that sense that the universe is an energetically open system, which drives not only the expansion, but also each individual particle oscillations. So, as we know, any oscillation can be described in non-equilibrium thermodynamics by a constant throughput of energy to be maintained. And so our answer is that the universe provides just such an energy that the particles are characterized by this frequency omega. And there's, of course, an analogy which is well known. It's related to the experiments by Yves Coudet's group in Paris on the bouncing oil drops on a vibrating bath. Where I just want to add that we use this only as an analogy which in several respects doesn't cover the whole model that we will try to develop. But still, it's a good analogy to start with, thinking about this in this direction. And one of the central ingredients which we also use is that there's a resonant interaction of some kind of bouncer with a relevant environment. And I'm going to talk immediately what could be meant by relevant environment. But let's turn back to quantum mechanics without wave functions in the literature. We heard this morning about Weizmann and other model where they show Bohm-type trajectories from a many classical worlds approach with certain repulsion effects between the trajectories. For us, we try to develop a different, based on the metaphysical assumption that I just mentioned, our model is one that one could call a superclassical world. That is a classical world with this kind of cosmological non-locality I referred to, which enters the definition of a quantum as the following thing, namely as an emergent system consisting of this bouncer and some wave-like non-local environment, which is defined by proper boundary conditions. This means, for example, just in a historical context, that this is not something like the nonlinear wave mechanics of de Broglie, which might superficially be meant by that, because there you also have a highly nonlinear part, and then the wiggling plane wave components. Because in de Broglie's ansatz, he wrote a book about that in the 60s. He considered the quanta as one ontic entity. I'm fine. Thank you. As one ontic entity, and we would rather see separate those synchronous elements, the local oscillations and the generally non-local oscillating fields. So here's where the Coudet analogy somehow applies. In our previous work, we derived the Schrödinger equation from a non-equilibrium subquantum dynamics, where the particle is a steady state with a constant throughput of energy. And in particular, we derived the often mentioned osmotic momentum today, independently from the ansatz of Nelson and the expression we have seen today several times, I think. So this brings us to the two-momentum approach to emergent quantum mechanics. A two momenta would be mv and mu, the forward momentum and the osmotic momentum. And we were able to show that, for example, wave packet evolution can be described classically as ballistic diffusion. The guiding law can be derived from this ansatz and shown to be emergent, but not predetermined. Jan this morning used these terms to differentiate between different approaches. And for us, the most exciting result is that we can show that there's no influence from configuration space necessary in this model, because the guiding equation can be derived in free space. Here's an example of what we did just for one Gaussian slit. We did both analytical calculations and computer simulations. And the analytical situations, velocity fields, acceleration fields, etc., are exactly the results that you obtain also in Bowman mechanics. And in the simulation scenario, I show here an example of a Gaussian and the Gaussian in a linear potential. We calculate the trajectories, but we also use our ballistic diffusion model to make simple classical simulations, and the trajectories are exactly the same. In the right-hand side picture, you can see that some bright blue spots. These are the trajectories from the simulation, from the calculation, and the black ones are the results from the simulation, so they are really identical. And they are the Bowman trajectories. It's important to note that we're not talking here about a particle, and then there's some field which you can turn on and off simply, but the particle and the field are permanently, dynamically interlocked. This is something which is very important for the emergent picture that we employ, because it's very often misunderstood in the sense that one is not, one doesn't take seriously the effects of the interlocking between the particle and the field at any time, because they usually influence each other at every time step, and we shall see something about that later on. So, one consequence of this is that the velocities or momenta are emergent. So, let's go from one slit to a double slit, where we have predetermined velocities, which means you have a particle plane wave coming in with k and splitting up in Ka and Kb, which also relates to two velocities, Va and Vb. And now we have this interaction, which we indicate like this. So if you introduce the osmotic momentum, which essentially is the gradient of the probability density distributions, then at each time step you have an update of the trajectory, which in the end provides not the predetermined velocities which you see on the top level, which are just straight lines due to momentum conservation, but much more complicated ones. And these are the ones we see, the trajectories that we see in the bottom level, and they are exactly identical to the Bohmian ones, although in our understanding these are average trajectories. So we suppose a more stochastic propagation, and the averaging provides these straight lines, which are then identical with the Bohmian ones. So due to the resonant coupling of the particle with the oscillations of the vacuum, which it's likely to be the zero-point vacuum filling the whole experimental setup, we employ non-local probability density distributions. So, for example, in a typical Gaussian slit, you have this Gaussian, and then you have long wiggly tails throughout the whole apparatus. So this is, so to say, the ansatz which brings non-locality in by hand. But we argue that in order to have a non-local theory, you have to put non-locality in. You don't get non-locality by putting in only local elements. So with this ansatz, we explain the end-slit interference. As I mentioned, we have the forward and the osmotic currents, and the only other quantity that we need in order to describe that are so-called relational intensities, where W now stands for either V or U. It's just a bookkeeping thing. And these relational intensities, oops, oh yeah, okay. So the usual formulation of the de Broglie-Bohm guidance equation, Bohm himself called it indigestible, this influence from configuration space on a particle in real space. However, the guidance equation is completely understandable in real coordinate space using, here we go, the relational intensities. And here's the definition. Basically, this is just the intensity at one slit plus all the interferences from the other slits with that particular slit. And if you do that, we derived an equation for the emergent velocity field, which is this very short line. And you can make it longer, like the last one. That's the quantum mechanical version of it. And in the middle line, we have an example for two slits, which is exactly identical to the Bohmian velocity field. So this, of course, is the guiding equation in different forms. But we think that ours looks quite short and elegant. And the price, of course, is that you have to use these relational intensities, which are non-local by themselves. So here are a few pictures from our simulations. As I said, these are, so to speak, classical, or rather super classical simulations on the computer, and we get practically the same trajectories as in Bohmian theory. There's interference with weak dispersion and a phase shift. You can add different average velocities, different spreadings, different probability densities, initial probability densities. Here is an n-slit situation with trajectories as we know them from Bohmian theory, and the Talbot effect.
Sorry, can you go back?
This one?
Yeah.
Okay, it's on the net. You can download it there. Or, I mean, this is a playground for simulations. For example, you can have gradually diminishing weights and play around, and it's a very simple computer model, and you really can provide, well, all stationary problems and simulate them. So here's the Coudet analogy once more. As I said, we have a resonant interaction with a relevant environment. What is that? Well, for very idealized non-interacting particles, this environment would be the whole universe. And for any particle in an experimental setup, it would be defined by the boundary conditions of the apparatus. So if you start with the whole universe and some indefinite order, if you build up an experiment, or later if we switch something in that experiment, what we do is introduce or change boundary conditions which immediately affect the fields V and U. And that's what we call vacuum landscaping. So these two fields must be related to the probability density, which of course is how they are practically defined, U at least. And changing the conditions on these fields would then mean that you change the vacuum structure of the whole apparatus, and that would mean that you can provide some influence by this type of switching. What we call systemic non-locality is just this way of switching from one relevant environment into another. The essential thing is that the switching of the apparatus elements, particularly the changing of the boundary conditions, involving source and detector, entails no propagation, and also, of course, no superluminal propagation, and no signals. I just put it here, and then maybe in the discussion we can go into detail. The bouncer jumps in our model from one cosmological solution to another, so there is not some origin from which, when you switch, something is propagating and bringing that influence to some other place. So this violates Gisin's principle of continuity, but because he was considering also the option of V-causality, that is that this influence in, for example, EPR type scenarios would propagate with velocities much larger than the speed of light, V being a tremendously big number. arguing that it would still follow a principle of continuity, of some kind of propagation. And he argued that, forgive me if I say something wrong, he argued that you can either have V causality with superluminal signaling or real physical non-locality. And of course, we argue for the latter part, that the non-locality is the reality that we are faced with. About the examples, I might talk later. Maybe we can finish now and start some discussion.
Yeah, fine. Okay.
Okay.
Right. Well done. Thanks for